Hello students, welcome back to my YouTube channel Advanced Physics. As I have promised you that if you are a serious aspirant of JEE Advanced or JEE Mains, then you will find a few interesting questions in JEE Advanced level in this particular channel. So today also I have come up with a very interesting question of catenary problem. This particular problem I have taken from a very famous book for JEE Advanced preparation, which is called Pathfinder. So before solving this question, guys, I want to tell you one thing that I personally believe that winners always go extra mile. That means you have to do something extra than others so that you can have an edge over others in that exam. And how to go this extra mile in physics? I have the answer for you. Come to my YouTube channel and you will find this type of questions where you can practice more and you can revise your concepts thoroughly. So today only we will not solve the question, but I will also provide you some extra practice problems. So be with me till the end of this video. You will find two more questions for your practice in the same topic. So first let us try to understand what the question statement is saying about. The question says that a uniform rope of length 12 meter is suspended between two fixed lanes A and B that are in the same horizontal levels. If the rope makes an angle theta equal to sine inverse 0.6 with the horizontal at the nails, then find the depth h of the lowest point on the rope below the nails and radius of curvature rho of the rope at the lowest point. So you can just take a try to solve this question for a few minutes and then again come back to this video and see what is my solution and whether your approach was correct or not, and if you have solved it in a different method, then don't forget to send me the solution so that I can share this with my students as well. So I hope that you have given it a fair try. And now let's see my solution of this question. This solution may be a bit lengthy because I tried to explain each and every small things. So without wasting any time, let's go to my solution. So this is the first slide where what I have done here, just look this picture of the same rope. I have taken it here, and at this middle point I have created my origin here of this x-axis and y-axis. Now what I have done, I have taken a very small element of this rope. That small element lies in between this x and dx segment and obviously in between y and dy segment. So the length of this small segment is dl. Now I want to analyze the forces acting on this small segment, and as you can see that I have mentioned this force is tension that is acting away from this small element, and this force is T plus dt. We know that in a massless and frictionless rope the tension remains same, but here the rope has a mass and that is why I have changed the tension slightly, and not only the tension is changing but also this angle which the tension makes with the horizontal line. You can see this angle also I have changed by a small delta theta amount. And also there is a weight acting downward of this small element. This weight is dm into g, where dm is the mass of this small element. Now before solving these equations, let us first understand a very basic assumption which is known as small theta approximation. In small theta approximation, we say that the sine of delta theta is equals to tan of delta theta equals to delta theta when delta theta is in radian and this is very small. And in this same approximation, we can say that cos of delta theta is equals to 1. So I will use these two approximations while solving this particular question. Let us first try to have a look on the horizontal forces acting on this small element. The horizontal force is T plus dt cos theta plus d theta minus T cos theta, and this net force should be 0 as there is no other horizontal force acting on this body. Now if I expand this cos of theta plus delta theta term, then you can see that it is cos A cos B minus sin A sin B. And what I have done, cos theta I have written as it is, but cos of delta theta I have made it 1 because of this approximation. Similarly, sin theta I have made it the same, but sin of delta theta I have made it only delta theta because of this approximation. Now you can multiply these terms, and you can see that it is t cos theta minus t sin theta d theta. D theta and delta theta, they are the same. Very small change in theta can also be written as d theta, and then dt cos theta minus dt sin theta d theta, and minus d cos theta, that is equal to 0. Now one thing you can also understand that this dt sin theta into d theta, this is product of two infinitesimally small quantities, dt as well as d theta. So I can neglect it to be 0, and you can say that t cos theta and t cos theta gets also cancelled out. So the final term that we are left with is dt cos theta is equal to t sin theta d theta. That is my equation number 1. That equation I have got from horizontal equilibrium condition. Now let us have a look on the vertical equilibrium of this rope, and this vertical equilibrium says that the vertical force is T plus dt sine of theta plus d theta, and its vertical force is T sine theta. So this minus sine theta is equals to dm into g. Now again, if I expand this sine theta plus delta theta term, you can see it is sine A cos B plus cos A sine B, and I have used the approximation just like the last calculation, and you can see that if I multiply these terms, then I am getting this entire result, and again I can neglect this dt and d theta term because of this small elements, and sin t sin theta gets cancelled out. So I am left with this one, dt sin theta plus t cos theta d theta is equals to lambda into dl into g. Now what is lambda here? I have assumed lambda to be mass per unit length. Mass per unit length of this rope, this is a constant because the rope is uniform. So I have assumed it to be lambda, mass per unit length. So this is our second equation that we have got from this vertical equilibrium. Now all these two equations we have directly got by analyzing this free body diagram and solving this mathematics. But again, there is an easier way to get these two equations. Just have a look on this alternate way. I am sure that you can also understand that alternate method. Now in this alternate method, what I have done, instead of writing these components separately, what I have done, I have taken that this vertical component is ty and horizontal component is tx here. So here the horizontal component will be tx plus dtx, a small change I have taken here, and also in vertical direction I have taken a small change in ty. So when I equate the horizontal forces, you can see tx and tx gets cancelled out, only dtx will become 0 here, and for vertical forces only dty will balance dmg. So these two equations I can write. And also what is tx? Tx is nothing but t cos theta, and ty is nothing but t sin theta. So when I am doing this d of t cos theta, then it is dt into cos theta minus sin theta d theta into t. And this is the first equation, which was exactly the same when we have solved it in this method. And in the second equation, dty is balancing dmg. So dty is equals to d of t sin theta, that is equal to dm into g, and d of t sin theta is t into cos theta d theta plus sin theta into dt, that is equals to lambda into dl into g, which is exactly the same equation that we have got here. So this is a shorter method to find the same equations, but this is only an alternate way to get those. I hope that up to this, this is clear to you, that how we have got these two equations by equating their horizontal and vertical forces on this particular body. Now let's come to the next part of the solution. Here I am trying to eliminate some t d theta from these two equations that we have already got. So this is the first equation that we have got in last slide, and this is the second equation that we have got in the last slide. And from these two equations, I am trying to eliminate t and d theta. So t d theta from the first equation is this one, and t d theta from the second equation is this one. When I am equating these two, then I am getting equation of dt only and dl here. And you can see that dt into cot theta plus tan theta is lambda dlg by cos theta. And again, if I simplify it, then cot theta plus tan theta is 1 by sin theta cos theta, and it is lambda dl by cos theta into g. So again, I can cancel cos theta from both the sides, and you can see that dt equal to lambda dl sin theta into g. Now, what is dl sin theta? That you can easily find from this small right angle triangle. Can you see that this right angle triangle has this hypotenuse dl? I have assumed it to be a straight line only because it's a very small part, and this angle is theta, so its horizontal component is dx and its vertical component is dy. So dl cos theta is dx and dl sin theta is dy. So we have dl sin theta here. I can directly replace dl sin theta by dy here in this equation. And if I integrate this from 0 to y and t1 to t2, then I can get an equation of t2 equal to t1 plus lambda g into y. Let us call this equation number 5. So in equation number 5, we have a relation between tensions at 2 points which are at a height separation of y. So now let us try to understand the free body diagram of this entire half of the rope. Now this is not an elemental portion, it is the right half of this rope that was hanging, and if I want to draw the free body diagram of this entire rope, then at the top there is a tension T2, and at the bottom or the lowest point there is a tension T1. The tensions I have drawn tangential to the rope. So at the lowest point the tension will be horizontal, and at the topmost point the tension will make an angle theta, which is given in our question. Now again, if I equate its horizontal and vertical forces, then I will get this equation for horizontal component, which is T2 cos theta equals to T1, and for the vertical equilibrium, I can say T2 sin theta is equals to mg by 2. Why half of the masses? Because this is only half part of the hanging rope, and mg by 2 is nothing but lambda g into L by 2. So these two equations I have got, and also I have got equation number 5, which says that T2 equals to T1 plus lambda into g into h, because here the y is nothing but h, the height separation between these 2 points. Now I have these 3 equations, I have to calculate h. So what I have done in this equation, I have replaced T2 from the second one here, and I have replaced T1 from the first one here, and then I have got the value of h in terms of L and theta only, and this is what I have got. I am not going into the detailed solution. I am sure that you can now solve these 2 steps by your own, and you have got the value of h in this form. And if you put the value of theta, sin theta equal to 0.6 here and L equal to 12 meter, then you will get the answer of this particular question is h equal to 2 meter. So this is the first answer to this question. I hope that you have understood this one. If not, then again go through each and every details of my solution, and definitely you will be able to understand this one. Now the next part of this solution is not difficult one. For it I will go to the next slide. Yes. So in this figure you can see I have taken a very small portion of the hanging rope which is at its lowest point, and this part is obviously a part of a circle, and the radius of this circle is the radius of curvature of this particular segment. That what I have to calculate in this question. So here the radius of curvature is this rho, and let us assume that at the center O, this particular segment has made an angle d theta, which is very small, of course. And when I draw the free body diagram, you can see the tensions are T1 and T1 in these two directions. T1 is the same tension that we have calculated in our last slide for the lowest point. And as this is a part of the lowest point, so I have taken the tensions to be the same, T1 and T1, and its vertical component is T1y, horizontal T1x, and T1x component gets cancelled out from both the sides because this is only horizontal forces, so they will cancel each other. But what is this T1y component? These two T1y components, it is balancing the weight of this small segment, which is dmg. So let me write down the equilibrium condition for this one. 2T1y is equal to dm into g. Now T1y, you can say it is T1 into sine d theta by 2. That is equals to lambda into dl into g. And what is sine d theta by 2? Here d theta is very small, so I can apply small theta approximation here, which is d theta by 2 only. And what is dl? This dl is the arc length of this circular portion, and that is rho into d theta. So if I solve it, you can see that 2 gets cancelled out, d theta gets cancelled out. So rho is equals to T1 by lambda g. And how to get this T1 in terms of theta and other given quantities? That already we have two equations from the last slide. Let me import those. Yes. So this was our last slide where I have drawn this particular segment, and T1 is equal to T2 cos theta and T2 sin theta is lambda GL by 2. If I just solve these two equations by eliminating T2, I can get the value of T1 to be this one, and I will just put this T1 value in this particular equation of rho, and the expression for rho becomes L cot theta by 2. So in this particular question, if you put the value of theta to be sine inverse 0.6, you will find the value of rho to be 8 meter. So that is my answer for this particular question. I hope the entire solution is clear to all of you. If not, then I will again suggest you to go through the detailed solution again, and definitely at the end of this video you should be able to solve the similar type of questions. For your practice purpose only, I will give you 2 more questions so that you can have a better understanding and you can build up your confidence to solve similar type of questions. So don't forget to send the solution in the comment box. If I see a good response from you, then I will definitely upload the video for the solution of those 2 questions in future again. So these are the questions. That's all for today, students. We will see in the next video very soon. Thank you.